So I see the count is going up and people are joining. So like 10, 20 more seconds and we will start. Okay, so good morning everyone, and we are about to open our track, the second track in AppSec Digital AppSec 2020. And first of all, I want to thank our gold sponsor, Amdocs and Checkmarks. You will hear that names a few more times today, and you can get more details about them in our sponsor page in appsec.org. So I want to say thank you as our opening speaker for this track to Eva Sarafianou. Sorry, I hope I pronounce it correctly. She's Greek, so almost similar. And few fun facts I learned while prepping for this session. You have your site, you have your blog, not always available. You should check that out. Yeah, I think it's offline. And you know your way in cryptography. That's awesome. Anyway, our session maybe is today different today, so the stage is yours. Have fun.
Thank you. Thank you for the intro. Let me share my screen. Okay, so I am Eva Sarafianou, and for the next almost 30 minutes, we will talk about browser storage, and more specifically about some security facts and fallacies around browser storage. And when we talk about browser storage and security, usually what we have in mind is how to protect against XSS. So we'll see it during the talk. I am a senior product security engineer at Auth0. Auth0 is an identity as a service platform for application builders and currently handles more than 2 billion logins per month. I'm also a part of the ecosystem security working group at Node.js. There I help with the bug bounty and the responsible disclosure program. And finally, I'm a member of the vulnerability disclosures working group at the newly found Open Source Security Foundation. What we'll talk about briefly is, first, we will discuss what are the different available browser storage options that we have and what security guarantees they offer in terms of protecting against XSS. We will spend quite some time in memory storage and different kinds of in-memory storage, and we will have an attack demo. And finally, we will discuss how we can improve in-memory storage utilizing web workers. Now, before we go to any of them, I just want us to refresh our memory around same origin policy, because we will use it later in the talk. So same origin policy is a very, very important security control of the browsers, because it restricts how one document or one script of one origin can interact with a resource of another origin. To say it more simply, how one web page can access another web page. And if we didn't have it, one web page could be able to access the DOM of another origin. And when we talk about origin in the same origin policy, we consider protocol, host, and port if it exists. If any of those three elements change, then we're talking about a different origin. And with that, we can move to our main topic for today. And we will start with a scenario, which is that we have Chloe. She's a front-end engineer, and product asked her to create a new feature that requires storing sensitive data in the browser. Now, Chloe is security aware and knows that some options are not secure, but she doesn't know which is the most secure and which is the one she should use. She reaches out to Irene. Irene is an AppSec engineer, and Irene says, no, never store such data in the browser. We need to find another design. Now, Chloe didn't really like this answer because there is no explanation. So she did her own research, and this is what we'll see today. First, let's see what are the different browser storage options. We have local storage, session storage, we have IndexedDB, cookies, and in-memory. And we will discuss each one of them separately. If we start with local storage offers isolation per same origin policy. So as we said, one origin cannot access the local storage of another origin. In local storage, the data are stored across browser sessions. And when we talk about browser session, we talk about when the user closes the tab or the window and then reopens it, the data are still there. Now, in terms of XSS, local storage doesn't offer much protection. An attacker can very simply get any secret value stored there by the code I have listed here. And it's important to note that the attacker doesn't need to know the key that is used in the local storage to store the secret. They may as well write a bit longer code that will retrieve all the key values of the local storage. So local storage is not a secure option. If we move to local storage, it's almost the same as local storage with a small difference. Again, it follows isolation per same origin policy. One origin cannot access the session storage of another origin. The difference is that when the page session ends, data are cleared. So when the user closes their tab, closes their window, data are cleared. Now, sometimes it's said that session storage is more secure than local storage exactly because data are cleared. And although I see like a reason why this can be said, in terms of XSS, it doesn't really change much. And the code I have listed here shows how we can retrieve the data from session storage. It's as simple as with local storage. Moving to the next one, we have IndexedDB. IndexedDB is a JavaScript-based object-oriented database where objects are indexed with a key. Now, again, what we care about is the level of isolation it offers, and this is, again, same origin policy. And we've seen from local storage and session storage that a same origin policy isolation doesn't protect us. The code I have put here is not to be read. It's only to showcase that it is still possible. It's a bit more complex for the attacker, but nothing that would stop them. And now that we've done those first three, we start getting to more interesting cases. And the first one is cookies. When someone tells me, let's store something sensitive value in a cookie, this information is not enough to determine, okay, this is a good option security-wise or not. And that's why we have to split them in HTTP-only cookies and cookies without this value. Now, for HTTP-only cookies, we can use them only if the secret is used in the backend. And this is because what HTTP-only says is that this cookie cannot be retrieved by the JavaScript. This is great because the attacker's JavaScript cannot get it, but this also limits the functionality that we can have around the secret because our front-end JavaScript can also not access the secret. Now, although the attacker in an HTTP-only cookie cannot retrieve the value, they can combine XSS with CSRF. So what they can do is, once they have the XSS, they can send a request to the backend, and the browser will happily include the cookie value to the request. This means that the attacker will be able to get back the data from the response. So to make it very clear, what HTTP-only cookies offer is that they protect the confidentiality of the secret, meaning that the attacker cannot take the secret value and use it offline, outside of the context of the XSS. Still, if they have XSS and they can use it with CSRF, they can get the results from the backend. Now, if we move to cookies without HTTP only, they can be retrieved by JavaScript, and it's as simple as the code I have listed there. So this is not an option if we're looking for a secure storage. Now let's talk about in-memory. And this slide is on purpose empty because in-memory is a very generic term that doesn't tell us enough about how we will actually store the secret value. We can have very insecure in-memory storage, and we can start building more secure in-memory storage. And to better showcase the different scenarios, the different cases of in-memory storage, I think the best way is to look at an example. And this is why I will move here. To explain first what this web page is about, this page is vulnerable to a DOM-based XSS. And to simulate this, we have here the XSS payload that the attacker can submit. And just to show that this works, I submit the XSS, I have alert 1. Now, here we have 2 different test cases, one in each line, but we will start with the first one. Here we have an input value, and let's say I have a super secret. When I click the submit button, this is the function that will run in JavaScript. So let me submit it and this run. Now, what this function does is that it gets the value of the element and it stores it into the secret_1 value. The secret_1 is defined at the top level of our JavaScript in the browser. And this is not secure. It's very easy for an attacker to retrieve the value, and it's actually as easy as asking for it. So if I submit this XSS, you can see that I get the super secret. The second example is slightly different. In this case, let me again write a value here, and I submit it, and this function runs. Here again, we retrieve the value of the element. Now we store it in a secret2 underscore variable, and then this variable is passed to a data object. What is important to note here is that secret_2 is defined within the scope of this function. However, the data object is again defined at the top level of our JavaScript. This means that if I go in my XSS payload and ask for secret2 and I submit XSS, nothing happens. And if I inspect and go to my console, you can see that we get an error that secret2 is not defined. The reason for this is that secret2 is defined only within this function, so it's not retrievable. However, we said that data is defined at the top level, so an attacker can access it. So if instead of secret_2, they type data secret, and they submit the XSS, they can get the value. Those first 2 are easy examples to show that just in memory is also insecure. Now, it is often said, and there is some truth there, that a way to protect in-memory storage is to use JavaScript private closures. And this is what we will see in those 2 examples. And I will walk through the code so you don't have to do it by yourselves. So first, to explain what is a private JavaScript closure. Our closure in this case is the fetch backend secret, because as you can see, this function is defined within the external function here. So we have this private closure, and within this private closure, we defined a variable called fetched secret. And what the next lines do is that they request the secret from the backend, and they assign it to the fetch secret. Now, since this function is not available to the outer JavaScript, in order to be able to run this function, what we do here is that we have this return value. And when we click this fetch secret, this is the function that runs. And more specifically, when I click the fetch secret button, we will run backend secret.value, because this will return this will execute the fetch backend secret. Now, if I fetch the secret, nothing happens. Now, how can an attacker still get the value that was retrieved, that we got from the response? This code that we have here has definitely some improvements to the previous code where we just had a variable available at the top level domain. We have used private closures. Private closures can emulate private functions, but we have an issue. We have used a function that is defined outside of the private closure, yet used within the private closure. And this function is the native JavaScript fetch. Fetch is not defined here. It's defined outside of the scope. So what an attacker can do is that they can override the fetch function to first reveal the secret value, the response to them, and then continue with the process. And this is what the payload I will paste here does, and I will explain it. So what we first do is that we keep a local copy of the window fetch, and we assign it to the fetch variable. And then we assign a new function to the window fetch. This new function, no need to get into every detail here, but actually it does the same thing as the fetch, the native fetch function, plus it, before it returns the promise here, it alerts on the response. So if I now first submit the XSS and then fetch the secret, you can see that I was able to get the response body that included the
Eva?
secret. Yes?
One question, sorry, one note that raised in the questions is that I think you share your browser, and when the pop-up dialog jump after an XSS, the attendees don't see it because
I'm
it's
so
not shared.
sorry.
No, no problem. If you can reshare the entire screen, it will be better.
Yes.
Oh, and the dog. That's nice.
Yes. So can you see it now?
Yes, we can.
I think I have time to just go through the previous ones again very quickly. Just to showcase, we have the super secret here, and thank you very much for the comment. We have a super secret here. We submit the secret, and I go in the secret _1, and you can see here. And with the second example, I submit the secret. Here I ask for secret 2. I submit. We said that nothing happens because we saw in the console that secret _2 is not defined because it's only defined within the scope of this function. However, if I change that and I do data secret and I submit the XSS, you can see the payload here, the secret value here. Now, if we move back to the example that we discussed before, this is the payload. Here I alert on the response body, and if I fetch the secret, you can see that I have retrieved the response body. What this example shows us is that if we have a single function that is defined outside of a private closure but is used within the private closure, we have an issue. There is one way to overcome it, but there are also like shortcomings to that. And this is the final example that we have. The only change between those two code snippets is that here we keep a local copy of the window fetch. So here we assign the window fetch to a local copy, and then we use this local copy to do the request. Because this local copy is defined within this function, the attacker cannot override the local fetch function. And even if they override the window fetch, this has run on load. So because here we execute the function. So this has run on load, meaning that even if the window fetch function changes, the local fetch function will not change. So again, if I already have this submitted, if I fetch the secret, nothing happens. And if I check at the inspect, you can see that nothing appears, and there is no way to retrieve the value. Now, seems good. What are the limitations? First, this is a very simple example. Imagine that we have a complex scenario within this code. We would need to keep a local copy for each single function that we use within the private closure. This becomes more complex, less clear code, but let's say we say, okay, still there is another issue, which is when we use third-party dependencies. Third-party dependencies have their own dependencies and so on. And we cannot, it's impossible to keep a local copy for them because they're not, it's like all the dependencies. So if your code uses a third-party dependency, this solution cannot be secure. An attacker can override any function from all the dependencies that are used to fetch to get the secret value. So if we go back to the slides, we see that in memory it's not so easy to get it correctly, and even if you think that you are protected against some versions, some attack payloads, there are more. And that's why I think at that point we went through all the different browser storage options. We have a problem in some cases. We don't have necessarily a good solution. And I think we need to take a step back. And we want to have a look at what we really want to do. And what we want, when we talk about having an XSS in our browser, we have an untrusted environment. We can no longer trust our JavaScript code that runs there. And what we're trying to do is to have some code that can handle sensitive data in this untrusted environment. Now, if we want to protect that, to protect those data, what we should be thinking is how we can isolate the code that is responsible for the sensitive data and any functionality around them from the rest of the untrusted environment. And to show this with a diagram, this is what we're looking for. We're looking for something that is a safe world. We have the unsafe world, and we usually need a channel between them where they can exchange any data needed from one to the other. And because we're talking about browsers, let's be more specific. What we're looking for is what different browser sandboxes we have as options. First one is Origin Sandbox. We've already discussed this. Origin Sandbox is local storage, session storage, IndexedDB, and we've seen that this is not a secure option. We have JavaScript closures. We saw that there are some cases, if they are simple and if they don't use if they don't use functions defined outside, that this could be an option. And what we haven't discussed so far is Process Sandbox. And this is where web workers come into play. There is one very, very important requirement for using web workers to work correctly. Yes, I forgot this slide, sorry. So if we take the previous diagram and we applied in our case, our unsafe world is the JavaScript application, because we said that if we have an XSS, this is untrusted. Web workers run on a separate process, so this is why we can say that this is a safe world. And the way those two worlds communicate with each other in case of a web worker is with a message channel. So each time the JavaScript application wants the web worker to do something, it sends a message through the message channel, and the web worker will respond back. Now, what I started to say before is that there is a very important requirement for this setup to be secure. And this is that the rest of the browser application must not need the secret. And to go back to the diagram to make it very specific is the secret should live here, and there should be no way that it is passed back through the message channel, back to the JavaScript application. If this happens, an attacker can override what the message channel does to reveal the secret to them. So assuming that we can have this requirement, what we can do is that we can have in-memory storage within the web worker. And the web worker has to take care not only of storing the secret, but also within the web worker, we have to have all the functionality that needs the secret. Now, one functionality that we often have that needs a secret is making requests to the backend. This has the same issue as we discussed with HTTP-only cookies, meaning that making requests to the browser can also be requested by the attacker. So the attacker who controls our front-end JavaScript application can send a message to our web worker and say, hey, I want you to make a request to backend and give me back the response. And again, the level of protection we have here in the secret is we protect the confidentiality of the value of the secret. The value cannot be retrieved, and the attacker cannot get the value and use it offline without the context of this compromised web page. The question may be, okay, web workers and HTTP-only cookies seem the same. What is the difference? I think the difference is more in matters of what you are allowed to do in each case. And what I mean is that with HTTP-only cookies, your JavaScript application doesn't have access to the secret. That's full stop, only the backend. Whereas with web workers, you have more flexibility because you can have some functionality that lives within the web worker and makes use of the secret value. And this is most of the things I had to say today. And what I'd like to close are some final thoughts that we see that none of the options are great. They have limitations, and some of them are definitely insecure. And there are some cases where we can have some secure options like HTTP-only cookies. Well, there is the requirement that your JavaScript code doesn't need it. We can have JavaScript closures. Well, we need to make sure that there is no external function used there, or if it's used, we keep a local copy. And if we use a third-party function within the private closure, we cannot use a private closure. And finally, we saw the web worker scenario. And any solution that we want to consider as secure needs at least the HTTP-only cookie is a bit different because it's only for the backend. Any of the other two solutions, the main requirement is that we can isolate the code that handles and needs the secret. If we cannot isolate it, we cannot have a secure solution. And the last thing I want to say is that it's difficult to do it correctly, and maybe depending on your requirements, there is no secure solution. And there, I understand there is a risk assessment to be made, but we should always consider using a backend for frontend. We should always consider how we can redesign what we want to implement to store the secret in the backend. And with that, I'm very happy to answer questions. This is my Twitter. If you'd like to follow me, ask me any questions. And let me now open the Q&A so I can see all of your questions. So the first one is, regarding session storage, it will require your XSS to run within the same page of the stored data, so it significantly reduces the exposure. I'm not sure what you mean by iframe, because the session storage has, in terms of isolation, it's the same as local storage, meaning it's origin policy. And when we have an XSS, our attacker has access to our origin. Where we have a reduced exposure is when a user closes a tab and reopens it before our JavaScript code regenerates or fetches, or I don't know how. When our JavaScript code doesn't have a secret, there is a small window there where the secret doesn't exist in the session storage. Whereas in a local storage scenario, it would be there from the previous session. Is there any other question? I can wait a few more minutes.
Let's give it one more minute or two. If anyone have a question and want to ask it, raise your hand. You have a minute or two.
Want to stand out online? Go to Wix.com and create a professional website that
probably no more questions.
Yes. Thank you very much, Eva, for your time today. It was awesome.
Thank you for having
we
me
enjoyed it a
here.
lot. I learned. Have a great day.
You too.
Bye.